On September 5, 1977, a rocket lifted off from Cape Canaveral carrying a spacecraft that weighed 825 kilograms, ran on 470 watts of power, about the same as 5 incandescent light bulbs, and had an onboard computer with 69 kilobytes of memory. That computer had less processing power than the thermostat on a modern refrigerator. The spacecraft's antenna was a dish 3.7 meters in diameter, and it communicated with Earth using a transmitter producing 23 watts of radio power, roughly equivalent to the signal strength of a typical refrigerator light bulb. That spacecraft is now the farthest human-made object from Earth that has ever existed. Voyager 1 is currently more than 163 astronomical units from the Sun, more than 163 times the distance from the Earth to the Sun, or approximately 24 billion kilometers. At that distance, a radio signal traveling at the speed of light takes more than 22 hours to reach Earth. When mission controllers at NASA's Jet Propulsion Laboratory in Pasadena send a command to Voyager 1, they must wait more than 22 hours for the signal to arrive, and then another 22 hours for any response to come back. A single round-trip exchange takes nearly 2 days, and yet despite the distance, despite the communication lag, despite the fact that Voyager 1 is operating on nuclear power from a generator that has been running continuously since 1977 and is now producing roughly a third of its original output, Voyager 1 is still working. It is still sending data. And the data it has been sending in the last decade, since it crossed a boundary that no human-made object had ever crossed before, has fundamentally changed our understanding of where the solar system ends and where interstellar space begins. That boundary is the heliopause. The heliopause is the edge of the heliosphere, the vast bubble of solar wind and solar magnetic field inflated by the Sun, extending billions of kilometers in every direction, that defines the Sun's sphere of direct physical influence. Inside the heliosphere, the dominant medium is the solar wind, the continuous stream of charged particles blown outward from the Sun at speeds of 400 to 800 kilometers per second. Outside the heliosphere, the dominant medium is the interstellar medium, the ancient, cold, magnetized plasma between the stars, shaped by a galaxy's worth of supernovae, stellar winds, and cosmic magnetic fields, flowing through the Milky Way on scales that make the heliosphere look like a grain of sand in an ocean. The heliopause is where these two media meet, where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium, where the Sun's direct physical reach ends, where, for the first time in the history of our civilization, a human-made object has crossed from one stellar environment into another. Voyager 1 crossed the heliopause in August 2012, after 35 years of continuous travel. Voyager 2 followed in November 2018, crossing the boundary at a different location with different instruments still functioning, giving us for the first time two simultaneous in situ measurements of the heliospheric boundary from different points in space. What they found was not what anyone expected. The boundary was sharper than predicted. The magnetic field behaved differently than models had assumed. The energetic particle environment changed in ways that challenged decades of theoretical work. And beyond the heliopause, in the region now confirmed to be genuine interstellar space, the two spacecraft found a medium that was simultaneously familiar, made of the same hydrogen and helium atoms and magnetic fields that theory had predicted, and deeply strange, with properties and structures that are still being worked out by scientists who have spent their entire careers trying to understand a region of space that no instrument had ever directly measured. This video is about what the Voyager spacecraft found at the edge of the solar system. It is about the structure of the heliosphere, how it forms, what maintains it, and what happens at its boundaries. It is about the specific data Voyager 1 and Voyager 2 recorded as they crossed the heliopause and entered interstellar space. And it is about what those measurements mean for our understanding of the solar system's place in the galaxy, the specific neighborhood of interstellar space that the sun and its planets are moving through right now as you watch this. Chapter 1: The Solar Wind. What inflates the heliosphere? To understand the heliopause, you first need to understand what inflates the bubble it is the boundary of. The heliosphere is inflated by the solar wind, a continuous supersonic outflow of charged particles from the sun's corona that streams outward in all directions at speeds of hundreds of kilometers per second. The solar wind is not a gentle breeze. It is a plasma, a gas of ionized atoms, primarily protons and electrons, with a smaller admixture of helium nuclei, alpha particles, and trace amounts of heavier ions. Moving outward from the sun at speeds that, at Earth's distance, average about 400 kilometers per second in the slow solar wind and 750 kilometers per second in the fast solar wind. These two components, the slow wind, originating primarily from the equatorial regions of the sun and from the boundaries of coronal holes, and the fast wind, originating from the open magnetic field lines within coronal holes, have different speeds, temperatures, and densities, and they interact with each other as the sun rotates, creating spiral structures in the interplanetary medium. The solar wind was predicted theoretically by Eugene Parker in 1958 in a paper that was initially rejected by referees who found the concept implausible. Parker's insight was that the corona, the sun's outer atmosphere, which reaches temperatures of millions of degrees, cannot be in hydrostatic equilibrium with the interstellar medium. The thermal pressure of the corona at such extreme temperatures drives a continuous outflow that cannot be contained. The corona must be expanding continuously, and the expansion must be supersonic at some distance from the sun. Parker's prediction was confirmed by the first direct measurements from spacecraft in the early 1960s. Luna 1 in 1959 detected plasma flowing outward from the sun, and the Mariner 2 spacecraft in 1962 definitively confirmed the continuous solar wind during its voyage to Venus. The practical consequences of the solar wind for the Earth are profound and direct. The solar wind carries charged particles that, when they interact with Earth's magnetic field, produce the aurora borealis and aurora australis. It strips away planetary atmospheres over geological time. Mars lost most of its atmosphere, partly because it has a weak magnetic field that does not deflect the solar wind effectively. It creates geomagnetic storms when intense bursts of solar wind, coronal mass ejections, slam into Earth's magnetosphere, potentially disrupting power grids satellite operations, and communications systems. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, was caused by a coronal mass ejection that arrived at Earth in minutes and produced auroras visible at tropical latitudes. A Carrington-class event today could cause trillions of dollars in damage to the modern technological infrastructure that depends on satellites and power grids. Understanding the solar wind, including its properties at the largest scales, as the Voyager data provides, is not merely academic. It is a practical requirement for understanding and mitigating space weather risk. At Earth's distance, 1 astronomical unit from the Sun, the solar wind has a density of approximately 5 to 10 protons per cubic centimeter. This sounds extremely thin, and it is. A cubic centimeter of Earth's atmosphere at sea level contains approximately 2.7 times 10 to the power of 19 molecules. The solar wind at Earth is about 3 quintillion times less dense than Earth's air. But it is moving very fast, and it carries with it the Sun's magnetic field. The Sun's magnetic field does not stay near the Sun, because the solar wind carries the solar plasma outward at supersonic speeds, and because the plasma is a good electrical conductor, charged particles move freely through it. The solar magnetic field is frozen into the plasma, carried along with it as it expands outward. As the Sun rotates, once every approximately 27 days at the equator, the magnetic field lines are wound into a spiral. The Archimedean spiral shape first described by Eugene Parker and now called the Parker spiral. The solar magnetic field at Earth's distance makes an angle of roughly 45 degrees with the radial direction from the Sun. At Voyager's distances, tens of astronomical units, the spiral is nearly perpendicular to the radial direction, wrapping around the solar system like the grooves of a record. This expanding solar wind, carrying the Sun's magnetic field outward in all directions at supersonic speeds, is what inflates the heliosphere. The heliosphere is not an empty bubble. It is a region of space filled with the solar plasma and the Sun's magnetized wind, extending outward until the dynamic pressure of this wind is balanced by the pressure of the interstellar medium pushing inward. The size of the heliosphere is not fixed. It fluctuates with the solar cycle, the approximately 11-year cycle of solar activity in which the Sun alternates between periods of intense magnetic activity, solar maximum, with many sunspots, flares, and coronal mass ejections, and relative calm, solar minimum, with fewer of these events. During solar maximum, the solar wind output increases and the heliosphere expands. During solar minimum, the output decreases and the heliosphere contracts. The fluctuations in heliospheric size are not small. The heliopause can move by perhaps 10 to 20 astronomical units over the course of a solar cycle. There is also a directional asymmetry. The Sun is not stationary. It is moving through the local interstellar medium at approximately 26 kilometers per second in a direction toward the constellation Hercules, a point called the solar apex. This motion compresses the heliosphere on the upstream side, the direction the Sun is moving toward, sometimes called the nose of the heliosphere, and stretches it into a long tail on the downstream side. The heliosphere is not a sphere, but a roughly comet-shaped structure, with the nose at perhaps 100 to 120 astronomical units from the Sun, and the tail extending to at least several hundred astronomical units, and possibly much farther. Voyager 1 and Voyager 2 both crossed the heliopause on the nose side, the upstream side, in the general direction of the solar apex, which is why they reached the heliopause at distances of approximately 122 and 119 astronomical units, respectively, consistent with models of the heliosphere's structure in that direction. The structure of the heliosphere between the Sun and the heliopause is not uniform. At some distance from the Sun, roughly 75 to 100 astronomical units, depending on direction, the solar wind undergoes a dramatic transition called the termination shock. This is the boundary where the solar wind, which has been flowing outward supersonically since it left the Sun, decelerates to subsonic speeds. The transition is sudden, a shock front, like the bow wave of a supersonic aircraft, and it is associated with a dramatic increase in plasma temperature and density and a corresponding decrease in wind speed. The region between the termination shock and the heliopause is called the heliosheath. It is a thick, turbulent region of compressed, hot, slowed solar wind plasma, a buffer zone between the solar wind proper and the interstellar medium. The heliosheath was traversed by both Voyager spacecraft before they reached the heliopause. Voyager 1 crossed the termination shock in December 2004 at a distance of approximately 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at a distance of approximately 84 astronomical units. The fact that they crossed at different distances reflected the asymmetry of the heliosphere. It is not perfectly symmetric, and the heliosheath is thicker in some directions than others. After crossing the termination shock, both spacecraft traveled through the heliosheath for years. Voyager 1 for approximately 8 years, Voyager 2 for approximately 11 years, before finally crossing the heliopause into true interstellar space. The heliosheath turned out to be a scientifically fascinating and theoretically challenging environment, with unexpected properties that continued to surprise the Voyager science team throughout the crossing. Chapter 2: The Termination Shock, where the solar wind hits the wall. The termination shock is not a wall in any physical sense. It is a transition, a sudden change in the state of the solar plasma that occurs when the outward flowing solar wind first encounters the resistance of the interstellar medium. Understanding the termination shock requires understanding why a supersonic flow must decelerate through a shock rather than gradually slowing. In a supersonic flow, information about conditions downstream cannot propagate back upstream. The flow is moving faster than the sound speed, so any signal generated by an obstacle ahead is overwhelmed by the flow and cannot reach back to warn the upstream material. When a supersonic flow must decelerate to match boundary conditions, as the solar wind must eventually decelerate to match the conditions at the heliopause, the deceleration cannot be gradual. It occurs abruptly in the shock front, where the plasma transitions from supersonic to subsonic in a thin region. Energy and momentum are conserved across the shock, but kinetic energy of bulk flow is converted to thermal energy. The plasma heats dramatically as it slows. Voyager 1 crossed the termination shock in December 2004 at 94 astronomical units. The crossing was confirmed by data from the plasma wave instrument, which detected the characteristic oscillations of plasma at the shock boundary, and by the magnetic field instrument, which recorded the sudden change in magnetic field magnitude and direction. The solar wind speed dropped from approximately 400 kilometers per second upstream of the shock to approximately 100 to 150 kilometers per second downstream, a deceleration to about a quarter of the upstream speed. The magnetic field strength roughly doubled. The plasma density increased. These are exactly the signatures expected from a perpendicular shock of the type theorists had predicted for the termination shock. But Voyager 1's crossing revealed a major surprise. The plasma instrument on Voyager 1 had failed in 1980, so its measurements of plasma velocity at the termination shock were indirect, inferred from other instruments rather than measured directly. When Voyager 2 crossed the termination shock in August 2007, its plasma instrument was still functioning, providing the first direct measurements of the solar wind speed and temperature at the shock. The plasma data from Voyager 2 confirmed the speed drop expected from theory, but revealed an unexpected feature. The energy of the termination shock did not all go where theorists predicted. In a standard shock, the thermal energy of the protons and the electrons behind the shock should be in a specific ratio determined by their mass ratio and the shock physics. The measured proton temperature behind the termination shock was lower than expected, significantly lower. Something was carrying away energy that was not appearing in the proton temperature. The leading hypothesis was that pickup ions, interstellar neutral atoms that drift into the heliosphere, become ionized by solar UV radiation or charge, exchange, and are then swept up by the solar wind, where the energy sink. Pickup ions are a minor component of the solar wind by number, but they are energetically significant. They have a different velocity distribution from the core solar wind ions. They are scattered across a broad range of energies rather than streaming uniformly outward. And they interact with the shock differently. The Voyager 2 data suggested that pickup ions were being preferentially energized at the termination shock, absorbing a significant fraction of the shock's energy, leaving the core solar wind protons cooler than expected. This pickup ion energization at the termination shock has implications that extend beyond the local heliospheric physics. Energetic pickup ions that are accelerated at the termination shock are one of the sources of anomalous cosmic rays. Cosmic ray particles detected at Earth with energies in the range of 1 to 300 megaelectron volts per nucleon that are distinct from the higher energy galactic cosmic rays arriving from outside the heliosphere. Anomalous cosmic rays were known from previous spacecraft measurements to have compositions consistent with ionized interstellar neutrals, helium, nitrogen, oxygen, neon, the same species that would be picked up from the interstellar medium. The hypothesis that they are accelerated at the termination shock had been the standard explanation, and the Voyager termination shock crossings were expected to definitively confirm it by detecting the acceleration process directly. What they found was more complicated. The anomalous cosmic ray fluxes did not peak at the termination shock itself. They continued to increase in the heliosheath beyond the shock, and were still increasing when Voyager 1 crossed the heliopause. The maximum anomalous cosmic ray flux was not at the termination shock, but somewhere in the heliosheath, or possibly at the heliopause itself. The termination shock was apparently not the primary acceleration site after all, or it was not the only site. The question of where anomalous cosmic rays are primarily accelerated remains an active area of research, with models invoking acceleration throughout the heliosheath and possibly at the heliopause itself. Chapter 3: The Heliosheath, the strange buffer zone. Between the termination shock and the heliopause lies the heliosheath, a region of compressed, decelerated, thermally energized solar wind that acts as a buffer between the supersonic solar wind and the interstellar medium. Both Voyager spacecraft spent years traversing the heliosheath, and the data they collected during this traversal revealed a region of extraordinary complexity and unexpected behavior that theoretical models had not anticipated. The most striking feature of the heliosheath is its temperature. When the solar wind crosses the termination shock and decelerates, its kinetic energy is converted to thermal energy. The protons heat up dramatically. The expected proton temperature in the heliosheath was in the range of millions to tens of millions of Kelvin, making it one of the hottest regions in the solar system by temperature, though not by energy density, since the density is extremely low. The Voyager measurements confirmed that the heliosheath is indeed a hot plasma, but the detailed temperature profile was not as simple as models predicted. The plasma appeared to be patchy and structured, not the smooth, well-mixed medium that simple models envisioned. One of the most remarkable discoveries in the heliosheath was the detection of large-scale magnetic structures called sector boundaries, regions where the magnetic polarity of the solar wind reverses. The Parker spiral magnetic field has sectors of alternating polarity separated by the heliospheric current sheet, a thin surface that wraps around the solar system like the skirt of a ballerina. In the inner heliosphere and at Earth's distance, the current sheet is relatively thin and the sector boundaries are clean transitions. But in the heliosheath, Voyager data showed that the sector boundaries were extremely complex, folded, compressed, and mixed by the dynamics of the heliosheath, creating a tangle of magnetic structures unlike anything in the inner solar system. Voyager 1 also detected something unexpected in the heliosheath, a region near the heliopause where the solar wind appeared to stagnate. In 2010, approximately 2 years before it crossed the heliopause, Voyager 1's data showed that the outward velocity of the solar wind had dropped essentially to zero. The plasma was no longer flowing outward. The instrument team initially feared this might indicate an instrument malfunction, but subsequent analysis confirmed the measurement was real. The solar wind had stalled. It was no longer moving radially outward from the sun. This stagnation region was a major surprise. It implied that the heliosheath was not simply a decelerating outflow of solar wind heading toward the heliopause. It was a region where the solar plasma was being deflected by the magnetic field at the heliopause and was flowing sideways around the heliopause toward the heliospheric tail. The solar wind, having decelerated at the termination shock, was being diverted into a flow that runs along the heliopause boundary rather than through it. This deflection is consistent with what happens when a supersonic to subsonic flow meets a curved, pressure-supported boundary. The plasma is swept around the obstacle rather than piling up against it, But the stagnation region's properties, its thickness, the degree of stagnation, the nature of the magnetic structures within it, were more dramatic than any model had specifically predicted. The heliosheath data also revealed variations in the flux of anomalous cosmic rays that suggested large-scale time variations in the heliosphere. As the solar cycle progressed, changes in the solar wind output and the heliospheric magnetic field propagated outward through the heliosphere as disturbances, eventually reaching Voyager's location in the heliosheath years later. The heliosheath is not a static environment. It evolves on timescales of years as the solar wind output changes, and the Voyager data provided a direct observation of these temporal variations at unprecedented distances from the Sun. Chapter 4: The Crossing. How we knew Voyager had left the solar system. On August 25, 2012, Voyager 1 crossed the heliopause and entered interstellar space. But determining that this had actually happened, that Voyager had crossed the boundary rather than simply passed through some unusual heliosheath structure, required careful analysis of data from multiple instruments. And the conclusion was not unanimous within the Voyager science team until several months after the fact. The challenge was that the heliopause is not physically marked. There is no sign, no visible boundary, no obvious physical discontinuity that would announce the crossing unambiguously to an instrument designed to measure plasma, magnetic fields, and energetic particles. The crossing had to be inferred from changes in the data, specific patterns of change across multiple instruments that, taken together, were consistent with having crossed the heliopause and inconsistent with any other explanation. There were 3 principal datasets that together established the crossing. The first was the cosmic ray data. Galactic cosmic rays, very high energy particles, mostly protons and heavier nuclei, that arrive at the solar system from sources distributed through the galaxy, are partially excluded from the inner heliosphere by the Sun's magnetic field and the solar wind. The heliosphere acts as a partial shield against galactic cosmic rays. The outward flowing solar wind makes it harder for cosmic rays to penetrate inward, and the heliospheric magnetic field deflects some fraction of them. Outside the heliopause, galactic cosmic rays should be at their undisturbed interstellar level. Inside, they should be partially suppressed. When Voyager 1 crossed the heliopause, the flux of galactic cosmic rays rose abruptly and dramatically, increasing by a factor of approximately 2 within a few days, and then plateaued at a stable, higher level. This was the signature of crossing from a region where galactic cosmic rays are partially excluded into a region where they are not excluded at all. The crossing was sharp. The transition from partially excluded to fully present took less than a week. The galactic cosmic ray flux after the crossing was consistent with the levels predicted by models of the interstellar cosmic ray environment. Simultaneously, the anomalous cosmic ray flux, the lower energy cosmic rays produced within the heliosphere, dropped sharply, essentially disappearing. Anomalous cosmic rays are a product of heliospheric physics. They should not exist in the interstellar medium beyond the heliopause. Their disappearance, simultaneous with the increase in galactic cosmic rays, was a strong indicator that Voyager had crossed the boundary. The second dataset was the magnetic field. If Voyager had crossed the heliopause, the magnetic field direction and magnitude should change. The heliospheric magnetic field is different in orientation from the interstellar magnetic field. The magnetic field data showed a change in magnitude. The field got stronger after the crossing, and evidence of a change in the large-scale structure, though the detailed direction change expected from models was not as clear-cut as some theorists had anticipated. The heliospheric and interstellar magnetic fields appeared to be more closely aligned at the crossing point than some models had predicted, which was an interesting result in itself. The third and most dramatic dataset was the plasma wave measurement. The plasma wave instrument on Voyager 1 measures the oscillations of electrons in the plasma. The electron density of the plasma can be inferred from the frequency of natural oscillations called plasma oscillations. The electrons in a plasma oscillate at a frequency proportional to the square root of the electron density. By listening to these oscillations, the plasma wave instrument can measure the plasma density. In the heliosheath, the plasma density is very low, roughly 0.001 electrons per cubic centimeter. In the local interstellar medium, density models predicted it should be much higher, perhaps 0.1 electrons per cubic centimeter, a factor of 100 higher. But measuring this directly required a perturbation of the plasma, a disturbance that would excite plasma oscillations at the local frequency. The perturbation arrived in April 2013 from a solar event in 2012. When the Sun produces a large coronal mass ejection or intense period of solar activity, it sends a pressure wave, a disturbance in the solar wind, propagating outward through the heliosphere. This wave eventually reaches the heliopause and beyond, driving oscillations in the plasma on both sides of the boundary. When the wave reached Voyager 1's location, now in interstellar space, in April 2013, it excited plasma oscillations. The Voyager plasma wave instrument recorded these oscillations and measured their frequency. From the frequency, the team calculated the local electron density. The result? 0.08 electrons per cubic centimeter. This was approximately 80 times higher than the density in the heliosheath, entirely consistent with the expected density of the local interstellar medium. This measurement definitively confirmed that Voyager 1 was in interstellar space. It was the first direct in situ measurement of the electron density of the local interstellar medium. The announcement was made in September 2013. Ed Stone, the Voyager project scientist who has served in that role since before launch in 1977, described the crossing as a historic milestone, the moment when humanity's reach first extended beyond the heliosphere into the space between the stars. There is a human dimension to this story that deserves its own moment. The debate within the Voyager science team about whether Voyager 1 had actually crossed the heliopause was real and substantive. When the cosmic rays shifted in August 2012, the abrupt increase in galactic cosmic rays and simultaneous drop in anomalous cosmic rays, some team members argued immediately that this was the heliopause crossing. Others were not convinced. The magnetic field had not changed direction as dramatically as some models predicted. There was no plasma measurement to anchor the interpretation. The features being observed could, in principle, represent some novel structure within the heliosheath. a magnetic barrier or depletion region, rather than a genuine crossing into interstellar space. The key to resolving the debate was the plasma oscillation measurement in April 2013. Without that measurement, without the direct determination of electron density from the plasma wave instrument, the crossing might have remained ambiguous for years. The solar activity event in 2012 that sent the pressure wave outward, arriving at Voyager 1's location in April 2013, was not planned by anyone at NASA. It was a natural event, occurring on its own schedule, and the timing of its arrival at Voyager, producing the plasma oscillations that settled the debate, was a piece of extraordinary scientific fortune. Nature itself provided the perturbation that the team needed to make the measurement that confirmed humanity had entered interstellar space. The boundary between scientific discovery and serendipity is rarely as clear as textbooks suggest, and the Voyager 1 heliopause crossing is a vivid illustration of that truth. Chapter 5: What Voyager 1 Found in Interstellar Space. The first direct measurements. After 35 years of travel and the crossing of the heliopause in August 2012, Voyager 1 entered the local interstellar medium, the specific region of interstellar space surrounding the Sun. The data it has been sending back since then represents the first direct in situ measurements of interstellar space ever made by any instrument. And the picture it reveals is both consistent with predictions and full of surprises. The local interstellar medium in the Sun's vicinity is not typical of the Milky Way as a whole. The Sun is embedded in a specific region called the local interstellar cloud, also known as the local fluff. A warm, partially ionized cloud of gas approximately 30 light-years across, through which the Sun has been traveling for roughly 100,000 years. The local fluff itself is part of a larger structure called the local bubble, a region of low-density, extremely hot gas, approximately 1,000 light-years across, thought to have been created by a series of supernova explosions over the past few million years. The Sun is near the interior edge of the local bubble, close to its boundary with the local fluff and other nearby clouds. The properties of the local interstellar medium as measured by Voyager 1 are broadly consistent with what remote observations had suggested. The electron density of approximately 0.08 electrons per cubic centimeter, measured from the plasma oscillations in 2013, is consistent with spectroscopic measurements of the local interstellar medium from Earth. The magnetic field strength in the interstellar medium near the heliopause, measured by Voyager 1's magnetometer, is approximately 0.4 to 0.5 nanoteslas, weak by any everyday standard, but consistent with the fields inferred from various indirect methods applied to the local interstellar medium. But the specifics of what Voyager found were not always what models predicted. The interstellar magnetic field direction near the heliopause was found to be more closely aligned with the heliospheric magnetic field at the crossing than expected, a finding that has implications for the large-scale structure of the heliosphere and the orientation of the heliopause relative to the interstellar magnetic field. Some models had predicted a sharp change in field direction at the heliopause. The data showed a more gradual transition in some components of the field, suggesting that the boundary region has more complex structure than simple models assumed. One of the most important measurements in interstellar space was the detection of what appears to be the signature of the electron density changing over time as Voyager moves through the local interstellar medium. Several plasma oscillation events, each triggered by a solar disturbance propagating outward through the heliosphere, have been detected since the 2013 measurement, each providing a snapshot of the local electron density at that moment and location. The density measurements have been slightly variable, suggesting that the local interstellar medium is not perfectly uniform. There is structure in the plasma density at scales of astronomical units to tens of astronomical units. This heterogeneity of the interstellar medium at small scales is an important observational result because most models of the interstellar medium treat it as smoothly varying on these scales. The galactic cosmic ray environment in interstellar space has also provided important data. Voyager 1's cosmic ray instruments have been measuring the cosmic ray flux both before and after the crossing, and the interstellar cosmic ray spectrum, the distribution of cosmic ray energies in genuine interstellar space, has been measured for the first time. One of the most interesting aspects of this measurement is the detection of low-energy cosmic rays, below about 100 mega-electron volts per nucleon, that are present in interstellar space, but were suppressed within the heliosphere by the solar wind. These low-energy cosmic rays had never been measured before because every previous cosmic ray detector was shielded from them by the heliosphere. Voyager 1 has now measured them directly, and their properties provide information about cosmic ray sources and propagation in the galaxy that was not accessible from inside the heliosphere. The energetic neutral atom ENA measurements from more recent spacecraft, particularly the Interstellar Boundary Explorer (IBEX), a small NASA satellite launched in 2008 specifically to study the heliospheric boundary, have complemented the Voyager in situ measurements with global maps of the heliopause region. IBEX measures energetic neutral atoms created when energetic ions in the heliosheath exchange charge with cold neutral atoms from the interstellar medium, becoming neutral and therefore able to travel in straight lines to the detector at Earth. These ENA maps provide a bird's eye view of the heliosheath and heliopause that the Voyager in situ measurements cannot. IBEX discovered an unexpected feature called the IBEX ribbon, a narrow band of enhanced ENA emission forming a partial arc across the sky, whose origin has been the subject of intense debate since its discovery in 2009. The ribbon's alignment with the local interstellar magnetic field strongly suggests that it is related to the interaction of pickup ions with the interstellar magnetic field at the heliopause, though the precise physical mechanism is not fully agreed upon. Chapter 6: Voyager 2's Crossing. A different perspective, a critical advantage. For 6 years after Voyager 1 crossed the heliopause in August 2012, Voyager 1 was alone in interstellar space. Voyager 2, traveling in a different direction at a slower rate, was still making its way through the heliosheath. Then, on November 5th, 2018, Voyager 2 crossed the heliopause at a distance of approximately 119 astronomical units from the Sun, a slightly smaller distance than Voyager 1's crossing at 122 astronomical units, reflecting the asymmetric structure of the heliosphere. The significance of Voyager 2's crossing cannot be overstated in terms of what it added scientifically. Voyager 2 has a functioning plasma instrument, the plasma science experiment, that Voyager 1 lost in 1980 when it failed. This plasma instrument directly measures the density, temperature, and velocity of the plasma, rather than inferring these quantities from other measurements. It means that Voyager 2's crossing of the heliopause was measured with a complete set of plasma diagnostics that Voyager 1's crossing lacked. The results from Voyager 2's crossing were published in a series of papers in Nature Astronomy in November 2019. A coordinated release of 5 papers covering different aspects of the crossing as measured by different instruments. Together, they painted a picture of the heliopause that was sharper and more precise than anything Voyager 1's data had allowed. The heliopause crossing itself in Voyager 2's data was remarkably abrupt. The solar wind plasma, which the plasma science experiment had been measuring for years, essentially stopped flowing outward within a day. The velocity of the solar wind dropped to 0. The galactic cosmic ray flux jumped. The magnetic field changed. The plasma density changed. All of these transitions happened within a few days of each other, at approximately the same position in space, consistent with crossing a thin boundary rather than a diffuse transition zone. The thickness of the heliopause, estimated from the duration of the transition and the spacecraft's speed, was remarkably small. The data suggested the heliopause was less than a few astronomical units thick, perhaps as thin as a single astronomical unit, or even less. This was surprisingly thin for a boundary between 2 plasma regions, each with their own magnetic fields and pressures. Standard magnetohydrodynamic models had suggested the heliopause should be a relatively sharp boundary, but the measured sharpness was at or beyond the sharp end of predictions. One of the most striking results from Voyager 2's crossing was the measurement of a thin layer of extremely hot plasma just inside the heliopause on the heliosheath side. This hot layer, with temperatures reaching tens of millions of Kelvin, far hotter than the surrounding heliosheath plasma, appears to be a thin boundary region where the solar and interstellar plasmas are mixing and the magnetic fields are reconnecting. Magnetic reconnection, the process in which magnetic field lines of opposite polarity break and reconnect, releasing energy as heat and particle acceleration, is a fundamental process in magnetized plasma physics, occurring throughout the heliosphere and in laboratories on Earth. Its detection at the heliopause provided direct evidence that reconnection is occurring at the solar system's boundary and contributing to the energy budget of the transition region. The interstellar magnetic field measured by Voyager 2 just outside the heliopause agreed well with the field measured by Voyager 1 at a different location, suggesting that the local interstellar magnetic field is relatively uniform over the distance between the 2 crossing points. But the direction of the interstellar magnetic field was found to be deflected by the presence of the heliosphere. The magnetic field lines are draped around the heliosphere, pushed slightly aside by the pressure of the heliospheric plasma. This draping of the interstellar magnetic field around the heliosphere is expected from models, but seeing it directly in the data confirmed the basic picture of the heliosphere as an obstacle in the interstellar medium that perturbs the local field structure. Perhaps the most unexpected finding from Voyager 2's crossing was the measurement of the interstellar plasma temperature. The plasma science experiment measured the temperature of the ions in the local interstellar medium just outside the heliopause. The value obtained was approximately 30,000 to 50,000 Kelvin, far hotter than the temperature typically assumed for the warm, neutral medium of the interstellar medium, which is around 6,000 to 10,000 Kelvin, but consistent with the warm, ionized medium. This relatively high temperature suggests that the region of interstellar space immediately outside the heliopause is primarily warm, ionized plasma rather than neutral gas, consistent with the picture of the local interstellar cloud as a partially ionized warm cloud. The comparison between Voyager 1's and Voyager 2's crossings also reveals something about the large-scale structure of the heliosphere. The two spacecraft crossed the heliopause at different distances, 122 astronomical units versus 119 astronomical units, and in different directions. Voyager 1 is heading in a direction roughly north of the ecliptic plane, while Voyager 2 is heading south. The slightly different crossing distances, combined with models of the heliosphere's shape, are consistent with the heliopause being somewhat flattened in the north-south direction and asymmetric in ways that reflect the interplay of the solar wind, the heliospheric magnetic field, and the local interstellar magnetic field. There is a deeper significance to having two crossing points rather than one that goes beyond the specific numbers. A single measurement, a single point in space at which the heliopause was crossed, tells you about the heliopause at that one location. Two measurements at different locations separated by tens of astronomical units and in different hemispheres of the heliosphere begin to tell you something about the heliopause as a structure. The fact that the interstellar magnetic field measured by both spacecraft is similar in magnitude and broadly consistent in direction tells you that the local interstellar medium has a roughly uniform magnetic field over the scale of tens of astronomical units, that it is not wildly variable at these scales. The fact that the crossing distances are slightly different constrains the asymmetry of the heliosphere. The fact that the magnetic reconnection signature was detected at both crossings, a thin, hot layer just inside the heliopause, suggests that reconnection is a general feature of the heliopause, not a local accident. The value of Voyager 2's functioning plasma instrument cannot be overstated. It is the instrument that directly confirmed what Voyager 1's plasma wave observations had inferred, that the plasma just outside the heliopause is significantly denser and warmer than the heliosheath plasma. It is the instrument that measured the hot layer at the heliopause crossing. It is the instrument that has continued to track the plasma properties in interstellar space as Voyager 2 recedes from the heliopause, providing a baseline for understanding how the interstellar medium varies with distance from the heliosphere. In many ways, Voyager 2's crossing was the scientifically richer of the two precisely because of this instrument. It filled in the gaps that Voyager 1's data had left, confirming interpretations that had been uncertain and revealing new features that single instrument inferences could not have uncovered. Chapter 7: The Heliosphere's Shape. More complicated than we thought. The shape of the heliosphere is one of the most actively debated topics in heliospheric physics. For most of the history of the field, the heliosphere was assumed to have a roughly comet-like shape. A roughly spherical upstream nose where the solar wind first encounters the interstellar medium head-on, and a long extended tail streaming away in the downstream direction of the sun's motion. This picture was motivated by the straightforward analogy with other examples of plasma obstacles in supersonic flows. The magnetospheres of planets, for instance, are compressed on the upstream side, the day side facing the solar wind, and extended into long tails on the downstream side. The comet-shaped heliosphere model was reinforced by early computer simulations of the heliosphere, which consistently produced an elongated downstream tail extending for hundreds to thousands of astronomical units. In this picture, the heliosphere is highly asymmetric, the upstream nose at perhaps 100 to 120 astronomical units, and the tail extending many times farther. Then, in 2017, a paper by Ofer and colleagues proposed a fundamentally different shape, a crescent or croissant shape, rather than a comet shape. The key ingredient in this new model was the specific geometry of the heliospheric magnetic field. As the solar wind flows outward in the Parker spiral, the magnetic field winds into a spiral that is different in the two hemispheres of the heliosphere. The northern hemisphere has a different polarity from the southern hemisphere, separated by the heliospheric current sheet. When this structured magnetic field is taken into account in simulations, the magnetic pressure in the heliosheath is not uniformly distributed. It is concentrated in specific regions that deflect the heliosheath plasma into two lobes, one in the north and one in the south, rather than a single symmetric tail. The resulting shape looks more like a crescent or a croissant than a comet. This debate about the heliosphere's shape is not merely aesthetic. The shape determines which parts of the interstellar medium the heliosphere is most exposed to, how cosmic rays penetrate the heliosphere from different directions, and what the pattern of ENAs observed by IBEX should look like. Different shape models make different predictions for the ENA sky maps. The IBEX data, with its detailed maps of the ENA emission from the heliospheric boundary, has been used to constrain the shape. But the data is complex enough that both the comet and croissant models can produce versions that are roughly consistent with the observations, with the differences concentrated in details of the tail region that IBEX cannot map well. The Voyager crossings provide one specific constraint on the shape: the nose of the heliosphere, where both spacecraft crossed, is at approximately 119 to 122 astronomical units, which is consistent with both models. The tail is much harder to constrain observationally. No spacecraft has crossed the heliosphere in the downstream direction, and no spacecraft is currently on a trajectory to do so. The tail of the heliosphere is estimated to extend to at least several hundred astronomical units based on models, but the actual extent, and whether it is a single elongated tail or two lobes, remains uncertain. The shaping of the heliosphere is also influenced by the properties of the local interstellar medium in a more fundamental way: the direction and magnitude of the interstellar magnetic field. If the interstellar magnetic field is strong relative to the ram pressure of the sun's motion through the interstellar medium, the field can significantly deform the heliosphere from its idealized shape. The Voyager measurements of the interstellar field, combined with IBEX measurements of the ribbon and other features, have been used to constrain the interstellar magnetic field direction, which appears to be approximately 30 to 40 degrees from the direction of the Sun's motion. This misalignment between the Sun's motion direction and the interstellar magnetic field direction is one of the factors that breaks the symmetry of the heliosphere and contributes to its asymmetric structure. Chapter 8: The Local Interstellar Cloud and the Local Bubble. The Sun's neighborhood Voyager 1 and Voyager 2 did not cross into some generic interstellar space when they passed through the heliopause. They crossed into a specific, named, studied region of the Milky Way, a neighborhood with identifiable properties and a documented history that spans millions of years. Understanding that neighborhood is essential for interpreting what the Voyager data means in the broader context of the Sun's journey through the galaxy. The immediate environment of the solar system is the local interstellar cloud, also called the local fluff. It is a small, warm, partially ionized cloud of gas roughly 30 light-years across, through which the Sun has been moving for approximately 100,000 years. The local fluff has a temperature of about 6,000 to 8,000 Kelvin, warm by interstellar cloud standards, and a density of roughly 0.3 hydrogen atoms per cubic centimeter, which is higher than the typical interstellar medium density, but very low by any terrestrial standard. Its partially ionized character means it contains a mixture of neutral and ionized hydrogen, with roughly equal amounts of each. The local fluff is not eternal. The Sun will exit it, based on current velocity estimates, in somewhere between 1,000 and 50,000 years. An extraordinarily wide uncertainty that reflects how difficult it is to determine the precise boundary of a diffuse cloud from inside it. When the Sun exits the local fluff and enters a different interstellar environment, the properties of the medium that interacts with the heliosphere will change, and the heliosphere will respond. Some models suggest that the heliosphere could either contract significantly if the Sun enters a denser interstellar medium, or expand if it enters a less dense region. The implications of such a transition for Earth's cosmic ray environment, and therefore potentially for climate and on the biological radiation dose at the surface, are an active area of research. The local fluff itself is embedded in a much larger structure, the local bubble. The local bubble is a region of extremely hot, extremely low-density gas approximately 1,000 light-years across, extending irregularly in different directions from the Sun. The gas in the local bubble has a temperature of approximately 1 to several million Kelvin, hot enough to emit X-rays, but is so diffuse, densities of 0.001 to 0.01 atoms per cubic centimeter, a factor of 30 to 300 less dense than the local fluff, that it contains very little total energy per unit volume. The origin of the local bubble was, until recently, controversial. The most accepted explanation was that it was excavated by a series of supernova explosions, stellar deaths that release enormous energy into the surrounding interstellar medium, vaporizing nearby gas clouds and blowing out a hot, low-density cavity. Given the size and energy of the local bubble, it would have required approximately 14 to 20 supernova explosions over the past 10 to 20 million years. In 2022, a major study led by Catherine Zucker at the Harvard Smithsonian Center for Astrophysics, published in Nature, used three-dimensional maps of dust and gas in the local interstellar medium, derived from Gaia satellite data to provide the most detailed picture of the local bubble's structure ever assembled. The study confirmed the supernova origin hypothesis and provided specific evidence for the sequence of events. The supernovae occurred roughly 14 million years ago when a cluster of massive stars, the progenitors of today's Scorpius-Centaurus OB association, the nearest OB association to the Sun, were reaching the end of their lives and exploding in rapid succession. The local bubble has been expanding from these explosions for 14 million years. Its current radius of approximately 500 to 1,000 light-years represents the current extent of the shell swept up by those ancient explosions. The most striking finding of the Zucker et al. Study was that the shell of the local bubble, the dense rim of swept-up gas at its boundary, contains nearly all of the major star-forming molecular clouds within a few hundred light-years of the Sun. The Ophiuchus, Lupus, Chameleon, Musca, Pipe, Corona Australis, and Taurus molecular clouds are all embedded in the shell of the local bubble. The local bubble's expansion is compressing the interstellar gas at its boundary and triggering the formation of new stars in the shells it creates. The Sun is embedded in the interior of a supernova-excavated cavity whose boundaries are the active nurseries for the next generation of stars. The Zucker et al. Discovery has a specific chronological elegance that is worth dwelling on. The supernova explosions that created the local bubble occurred approximately 14 million years ago. At that time, the ancestors of modern humans did not yet exist. The human evolutionary lineage was still at the stage of early Miocene apes. The expanding bubble of hot, low-density gas from those ancient stellar deaths was already well underway before anything that would eventually become a human being had drawn its first breath. The Sun has spent roughly the last 5 million years moving through the interior of this cavity. The cavity was already waiting, already established, when the first members of the genus Homo appeared. The molecular clouds currently embedded in the local bubble's shell, the clouds that Zucker et al. Showed were concentrated in the swept-up rim, are the Taichia, star-forming regions that will produce the Sun's stellar neighbors over the next few tens of millions of years. The Ophiuchus and Taurus molecular clouds, forming stars right now at distances of 450 and 140 light-years respectively, are producing stars from gas that was compressed by the same ancient supernova explosions that created the cavity the Sun is currently traversing. The past deaths of massive stars are triggering the births of the Sun's future neighbors. The heliosphere that Voyager is leaving is embedded in a cosmic structure whose history spans millions of years and whose future will unfold on similar timescales. The specific numbers here are grounding in the most vivid way. The Sun traverses approximately 26 kilometers of interstellar space every second. Over 1 year, this amounts to roughly 820 billion kilometers, about 5.5 astronomical units. Over 1 million years, the Sun moves approximately 5,500 astronomical units, just under 1/10 of a light year. The Sun has been traversing the local bubble for roughly 5 million years, having entered it from a denser cloud on the outside. In that time, it has moved approximately 130 light-years through the bubble's interior. The 30 light-year local fluff, the small, warm cloud the Sun is currently passing through, is one of several small cloudlets embedded in the bubble's interior, and the Sun has probably been inside it for only the last 100,000 years or so. Before that, it was in the hot, even more tenuous medium of the bubble's interior proper. When it exits the local fluff in the next few thousand to tens of thousands of years, it will re-enter the hot bubble interior before eventually encountering the dense shell at the bubble's edge. An encounter that, at the Sun's current velocity, is still millions of years in the future. This is the context in which Voyager is operating. The heliosphere that Voyager 1 and Voyager 2 exited is a structure that exists at the interface between the Sun's direct influence and the warm, partially ionized medium of the local fluff, which is itself embedded in the hot, supernova-blown cavity of the local bubble, whose expanding shell is triggering the star formation that will produce the Sun's stellar neighbors of the future. The Voyager data is not just data about the heliosphere's boundary. It is data about one specific point on the boundary between a star's private bubble and the galaxy-scale structures that surround it. The Sun is not a passive passenger in this environment. It is moving through it at approximately 26 kilometers per second relative to the local standard of rest, the average motion of the stars in the Sun's neighborhood. This motion means that the heliosphere is continuously plowing through the local fluff at this speed, experiencing the ram pressure of the interstellar medium flowing past its nose at roughly 26 kilometers per second in the Sun's reference frame. The direction of this motion toward the constellation Hercules is what defines the usual nose and tail orientation of the heliosphere and determines which direction the two Voyager spacecraft crossed the heliopause. As the Sun moves through the local fluff, the properties of the interstellar medium that the heliosphere encounters change gradually. The density, temperature, ionization state, and magnetic field of the medium vary over the distances the Sun traverses on timescales of tens of thousands to millions of years. Reconstructing the Sun's past interstellar environments from the properties of the local interstellar clouds and the Sun's trajectory through them is an active area of research that uses the Voyager data, Hubble Space Telescope spectroscopy of nearby stars, and models of the local bubble's dynamics to piece together the story of how the Sun's cosmic neighborhood has changed over geological time. Chapter 9: What the data means for the heliosphere as a cosmic ray shield. One of the most practically important questions about the heliosphere's interaction with the interstellar medium is how effectively the heliosphere shields the inner solar system and Earth from galactic cosmic rays. Cosmic rays are a potential hazard to life on Earth and are a well-established driver of ionization in the atmosphere that may affect cloud formation and possibly climate. Understanding how the heliospheric shield works and how it might change as the Sun moves through different interstellar environments is therefore a question with implications extending well beyond pure physics. Galactic cosmic rays are extremely high-energy particles, protons and heavier nuclei, that arrive at the heliosphere from all directions, produced by supernova shockwaves, pulsars, and other energetic sources distributed through the galaxy. They carry kinetic energies ranging from a few million electron volts to extreme values above 10 to the 20 power electron volts. The highest energies observed in any particle, far exceeding anything the most powerful terrestrial accelerator can produce. The lower energy galactic cosmic rays, below about 1 giga-electron volt, are strongly modulated by the heliosphere, significantly suppressed inside the heliopause relative to the interstellar level. Higher energy cosmic rays are less affected by the heliosphere because their large magnetic rigidity, the product of momentum and charge, makes them harder to deflect by the relatively weak heliospheric magnetic field. Voyager 1's crossing of the heliopause provided the first direct measurement of galactic cosmic rays in true interstellar space without the heliospheric modulation. The cosmic ray instruments on Voyager 1 measured the interstellar cosmic ray spectrum below about 300 mega-electron volts, energies that are heavily suppressed inside the heliosphere. For the first time, the interstellar flux at these low energies was approximately twice the flux measured in the inner heliosphere. This factor of 2 is the direct measured shielding effectiveness of the heliosphere against low energy galactic cosmic rays. The shielding is not trivial biologically. While high-energy cosmic rays, above about 1 giga-electron volt, penetrate the heliosphere with little attenuation and reach Earth's surface, primarily as secondary cosmic ray showers after interacting with the atmosphere, the lower energy component, now measured to be present at approximately twice the current terrestrial rate in interstellar space, is shielded by the heliosphere. A hypothetical organism in interstellar space outside the heliosphere would receive a higher cosmic ray dose than organisms on Earth's surface. However, the scale of the shielding difference, a factor of about 2 for the lowest energies, is not as large as one might naively expect from the heliosphere's role as the sun's protective bubble. This is partly because the bulk of the biological dose from cosmic rays comes from the higher energy particles which penetrate the heliosphere easily, and from secondary radiation produced in the atmosphere rather than from the low-energy component that the heliosphere most effectively modulates. The heliosphere's shielding is real, but not the difference between a habitable and an uninhabitable world. Earth's atmosphere and magnetic field provide far more effective protection for surface life than the heliosphere does. The question of how the heliosphere's shielding has varied over geological time is more interesting from an astrobiological perspective. If the sun has passed through denser interstellar clouds in the past, as it must have done given the variety of environments in its galactic neighborhood, the heliosphere would have been compressed by the increased external pressure. A smaller heliosphere extends less far from the sun and provides less modulation of the incoming cosmic ray flux. Earth would have received more galactic cosmic rays during periods when the heliosphere was compressed by a dense interstellar cloud. Reconstructions of the sun's trajectory through the local interstellar medium over the past few million years suggest that it may have passed through or near the edges of denser clouds. And some researchers have proposed connections between these passages and periods of enhanced terrestrial cosmic ray flux, potential climate effects through hypothesized cosmic ray cloud interactions, and even the timing of mass extinction events. the evidence for these connections is indirect, and the proposed mechanisms are debated. The relationship between cosmic rays and climate, in particular, is an active area of scientific controversy. But the Voyager measurements have provided the observational anchor that the theoretical discussions needed. The first direct measurement of how the heliosphere modulates the galactic cosmic ray flux, from which the shielding factor for different heliospheric configurations can be calculated. The geological record contains specific chemical signatures that may reflect variations in the cosmic ray flux reaching Earth's surface over deep time. Beryllium-10 and chlorine-36, cosmogenic nuclides produced when cosmic rays interact with oxygen and nitrogen in the atmosphere, are preserved in ice cores, sediment records, and ocean sediment. Measuring their concentrations over time provides a proxy record of the cosmic ray flux reaching Earth's upper atmosphere. These records show variations on timescales from decades associated with the 11-year solar cycle and its modulation of the heliosphere, to millennia and beyond, associated with changes in Earth's magnetic field, the heliosphere's history, and potentially the Sun's movement through different interstellar environments. The beryllium-10 record in ice cores extends back approximately 800,000 years, roughly 8 complete glacial-interglacial cycles. The record shows a strong correlation between low cosmogenic nuclide production, indicating low cosmic ray flux, indicating strong heliospheric or geomagnetic shielding, and warm interglacial periods and high production, high cosmic ray flux, weaker shielding during glacial periods. The interpretation of this correlation is contested. One school of thought argues that the correlation is driven by geomagnetic field variations. The Earth's magnetic field is weaker during some periods, allowing more cosmic rays through regardless of the heliosphere, while another proposes that the cosmic ray flux itself affects cloud formation and thereby climate, creating the correlation through physical causation rather than a common driver. The debate about cosmic ray climate links is one of the more contentious in climate science. What Voyager's measurements contribute to this debate is the anchor, a direct measurement of how much the heliosphere actually modulates the low-energy cosmic ray flux. The factor of roughly 2 measured at the heliopause, approximately twice as many low-energy galactic cosmic rays in interstellar space as inside the heliosphere, sets the scale of the heliospheric shielding effect. Models of how this shielding changes with the heliosphere's size, which varies with the solar cycle and with the properties of the interstellar medium the Sun is moving through, can now be calibrated against this direct measurement rather than relying entirely on theoretical estimates. There is also the question of anomalous cosmic rays, the heliospheric cosmic rays first mentioned in Chapter 2, whose acceleration mechanism the Voyager data has constrained but not fully resolved. Understanding where anomalous cosmic rays are accelerated is important for understanding the overall energetics of the heliosphere and the sources of low-energy particles that reach the inner solar system. The Voyager data showed that the anomalous cosmic ray flux was at its maximum near the heliopause rather than at the termination shock, suggesting that the heliopause region, or possibly the process of magnetic reconnection occurring at the heliopause boundary, is a more important acceleration site than previously thought. this remains one of the active areas of heliospheric theory directly motivated by the Voyager crossing data. Chapter 10: The Hydrogen Wall, a discovery at the frontier. Between the heliopause and the interstellar medium, there is a structure that no spacecraft has yet reached, and that only the Voyager instruments have begun to probe from the inside: the hydrogen wall. The hydrogen wall is a concentration of neutral hydrogen atoms that accumulates just outside and around the heliopause. It forms from a specific physical process. As the Sun's heliosphere moves through the interstellar medium, the neutral hydrogen atoms in the interstellar medium cannot simply flow around the heliosphere the way charged particles do. Charged particles are deflected by the heliospheric magnetic field. Neutral atoms are not directly affected by magnetic fields. However, neutral hydrogen atoms can interact with the solar, ultraviolet radiation and with the charged particles at the heliopause through charge exchange, a process in which a slow interstellar neutral hydrogen atom swaps its electron with a fast heliospheric proton, becoming a fast neutral and leaving a slow ion. The net effect of this charge exchange is that some interstellar neutral hydrogen atoms are slowed and compressed near the heliopause, forming a dense wall of neutral hydrogen just outside the heliosphere. This hydrogen wall acts as both a physical feature and an observable signature. From outside the solar system, any telescope sensitive to ultraviolet light at the wavelength of Lyman alpha, the characteristic ultraviolet emission line of neutral hydrogen, would detect the hydrogen wall as an excess of emission surrounding the heliosphere. The hydrogen wall was predicted theoretically before it was observed, but its existence was confirmed by the Hubble Space Telescope in the 1990s. Through observations of the Lyman alpha spectrum of light from nearby stars. When Hubble measured the ultraviolet spectrum of stars at distances of a few to tens of light years, the absorption of the stellar Lyman alpha light by intervening hydrogen showed a characteristic pattern, an extra component of absorption at a velocity consistent with neutral hydrogen slowed relative to the expected interstellar flow. This extra absorption is the hydrogen wall, a region of dense, decelerated neutral hydrogen wrapping around the Sun's heliosphere, detected in absorption against the background of nearby stellar emission. What makes the hydrogen wall particularly interesting is that it is not unique to the solar heliosphere. Any star with a stellar wind inflating a stellar astrosphere would have an equivalent feature, a wall of compressed neutral hydrogen wrapping around its astrosphere. And this feature is observable from astronomical distances using ultraviolet spectroscopy. In principle, the presence of an astrospheric hydrogen wall around a distant star is a remote sensing probe of that star's stellar wind and the properties of the interstellar medium in its vicinity. Brian Wood and colleagues at the Naval Research Laboratory have used Hubble Space Telescope ultraviolet spectroscopy to detect hydrogen walls around more than a dozen nearby stars, confirming that stellar astrospheres are common features around other stars, and that the heliosphere is not anomalous in this respect. The detailed properties of these extrasolar hydrogen walls, their strength, shape, and velocity structure, have been used to infer the stellar wind properties of the host stars. The Sun's own hydrogen wall provides a calibration point, a known case where both the hydrogen wall properties from Hubble spectroscopy and the heliosphere properties from Voyager in situ measurements are available, allowing the indirect stellar wind inference from hydrogen wall spectroscopy to be validated. The Voyager spacecraft are currently traveling through the heliosphere's interior hydrogen wall region, the diffuse region just inside the heliopause, where the interstellar neutrals begin to interact with the heliospheric plasma. The New Horizons spacecraft, which is further along its trajectory than is commonly appreciated. It is now beyond 60 astronomical units from the Sun, well into the heliosheath region, is also carrying an ultraviolet spectrometer that is measuring the Lyman alpha background and the properties of the heliospheric Lyman alpha glow. The cumulative measurements from Voyager, New Horizons, and the Hubble spectroscopy of nearby stellar hydrogen walls are assembling a picture of the heliosphere's outer environment that no single observation channel could provide. The full hydrogen wall structure, including its density, temperature, and velocity profile as a function of distance from the heliopause, has not yet been directly measured in situ. Voyager 1 and Voyager 2 are now well beyond the heliopause in the interstellar medium itself, and neither carries the instruments needed to map the neutral hydrogen density in detail. The hydrogen wall will remain, for the foreseeable future, a remotely observed feature of the heliosphere, rather than a directly measured one. Its full characterization will likely require a future mission specifically designed to probe the heliopause region with neutral atom detectors and ultraviolet spectroscopy, a mission that does not yet exist beyond the planning stage. Chapter 11: Voyager's Power Problem. How much longer do we have? In 1977, each Voyager spacecraft was launched with a radioisotope thermoelectric generator, an RTG, containing about 4.5 kilograms of plutonium-238 dioxide. The RTG converts the heat from the radioactive decay of plutonium-238, which has a half-life of 87.7 years, directly into electricity through the thermoelectric effect. At launch, each RTG produced approximately 470 watts of electrical power. The YAO spacecraft systems required a certain fraction of that power. The remainder was available for the scientific instruments. Plutonium-238 decays at a rate determined by its half-life. After one half-life of 87.7 years, half of the original plutonium will have decayed and the power output will be halved. In a time frame shorter than the half-life, the power decrease is roughly linear, approximately 0.79% per year. After 47 years of operation, the current age of both Voyager spacecraft, the RTGs are producing approximately 63% of their original power output, or roughly 296 watts. Of those 296 watts, a significant fraction is consumed by the spacecraft's basic functions. Heaters that keep critical components from freezing in the cold of deep space, the onboard computers that process and encode the science data and transmit it to Earth, the attitude control systems that keep the antenna pointed at Earth, and the radio transmitter that sends the data home. As the power has declined over the decades, the mission operations team at JPL has progressively shut down subsystems and instruments to ensure that the remaining power is sufficient to operate the systems that are most scientifically valuable. The heating is one of the less visible but critical power consumers. Deep space temperatures are approximately 2.725 Kelvin, the CMB temperature, and electronic components that operate at these temperatures without heating would be destroyed. The spacecraft's fuel lines, in particular, must be kept above a minimum temperature to prevent the hydrazine attitude control thruster propellant from freezing. Heaters that maintain these minimum temperatures are non-negotiable power loads. If the heaters fail, the spacecraft loses its ability to point its antenna at Earth, and communication is lost. By 2024, the remaining operational science instruments on Voyager 1 are 4: the cosmic ray subsystem, the low-energy charged particle instrument, the magnetometer, and the plasma wave subsystem. The plasma wave subsystem requires specific attention. It detected the plasma oscillations that confirmed the heliopause crossing and has continued to detect oscillation events in interstellar space. The magnetometer provides the direct measurement of the interstellar magnetic field as Voyager 1 moves through it. The cosmic ray subsystem measures the galactic cosmic ray flux in interstellar space. Together, these 4 instruments represent the irreducible minimum of the Voyager 1 science mission, the suite of measurements that provides continuous monitoring of the interstellar medium as Voyager recedes from the Sun. Voyager 2 retains a slightly different but overlapping suite of instruments, including its functioning plasma science experiment. The critical plasma instrument that Voyager 1 lost in 1980. As long as the plasma instrument continues to function, Voyager 2 is providing direct measurements of the plasma velocity and temperature in interstellar space that are unavailable from any other source. The operational lifetime of the Voyager spacecraft depends on how much electrical power remains, how efficiently the mission team can allocate it, and whether any critical component fails. JPL engineers have estimated that the last instruments could be kept running until approximately 2025 to 2030. Though this estimate has been revised repeatedly as the team finds innovative ways to extract additional operational life from the aging hardware. A specific challenge emerged in late 2023 when Voyager 1 began sending garbled data. A malfunction traced to a corrupted memory chip in the flight data system computer. The mission team, working with software and hardware documentation that is nearly 50 years old, managed to reroute the data around the damaged memory, restoring science data transmission. This near loss and recovery was a vivid reminder of how close the end is and how much expertise and ingenuity the small team at JPL has invested in keeping these spacecraft alive. The 2023 memory chip crisis deserves more detail because it illustrates the extraordinary nature of the Voyager operations challenge. In November 2023, the Voyager 1 flight data system, one of 3 onboard computers, began returning garbled data to Earth. The science and engineering data was corrupted. The bits arriving at JPL did not correspond to any recognizable information. Initial analysis suggested the computer was somehow stuck in a loop, repeatedly transmitting data from a single memory location, rather than cycling through all the scientific and engineering data packets. The investigation was complicated by the simplest imaginable operational fact. Any command sent to Voyager 1 takes 22.5 hours to arrive. Any response takes 22.5 hours to return. Diagnosing the problem, trying different approaches, observing the results, and iterating operates on a cycle of 45 hours per round trip. Engineers at JPL who discovered the anomaly in one working day would not know whether their diagnostic commands had produced any response until almost 2 days later. The team spent weeks sending commands and analyzing responses, gradually building a picture of what had gone wrong. The eventual diagnosis: a single chip in the flight data system memory had corrupted, preventing the system from reliably accessing the instructions stored in that memory location. The corrupted memory location affected the packaging of the science and engineering data, causing the garbled output. The chip itself could not be repaired. It is a physical component of hardware that is 46 years old and currently more than 24 billion kilometers from any human who could touch it. The solution required something that is almost never done with spacecraft software: rewriting code that is already in flight. The team identified all the data that had been stored in the corrupted memory location and redistributed it across other parts of the flight data system memory, rewriting the software to reference the new locations. This code modification had to be developed, tested on ground simulators, imperfect simulations of 47-year-old hardware, and then sent to the spacecraft in a careful sequence of commands, each with a 22.5-hour travel time. By April 2024, the team had successfully restored the transmission of engineering data, and by May 2024, the science data was flowing again. The mission was saved by engineers working with documentation from the Ford administration era, rewriting code for hardware that was built before the personal computer existed, for a spacecraft that cannot hear them for nearly a day after they speak. When the last instrument fails, or when the RTG power output drops below the minimum needed to maintain the heaters and the communication link, Voyager 1 and Voyager 2 will continue on their trajectories silently, no longer sending data back. They will be traveling through interstellar space for millions of years, gradually approaching other stars. Voyager 1, on its current trajectory, will come within approximately 1.7 light-years of the star AC plus 79 3888 in approximately 40,000 years. Voyager 2 will come within approximately 1.7 light-years of the star Ross 248 in approximately 40,000 years as well. A remarkable coincidence of timing, if not of destination. Neither will enter another planetary system, they will simply pass nearby. The closest human-made objects will ever come to another star. Each spacecraft carries a golden record, a phonograph record plated with gold, containing sounds and images from Earth, greetings in 55 languages, music from across human cultures, and 115 images representing life and civilization on Earth. The records were assembled under the direction of Carl Sagan and are intended as messages to any intelligent civilization that might encounter the spacecraft in the deep future. Whether any civilization will ever intercept them, given the incomprehensible distances and the essentially random trajectories of the spacecraft through the galaxy, is unknown. But the records are there. The encrypted sounds of a rainstorm, of a heartbeat, of Chuck Berry's "Johnny Be Good," and of greetings in ancient Greek and Swahili. are currently traversing interstellar space in a vacuum-sealed golden disk, moving at 17 kilometers per second on a journey that will not bring them near another star for longer than our civilization has existed. Chapter 12: What Comes After Voyager? The Future of Heliospheric Exploration. The Voyager data has transformed heliospheric physics and given humanity its first direct measurements of interstellar space. But the measurements have also revealed how much we still don't understand. How many questions the Voyager data has raised that it cannot itself answer. The next generation of heliospheric exploration is being planned, and the scientific questions it aims to address have been sharpened directly by what Voyager found and what it could not tell us. The most significant limitation of the Voyager data is coverage. 2 data points, 2 locations at which the heliosphere has been directly measured, are far too few to characterize a 3-dimensional structure as complex as the heliosphere. The heliopause has been crossed at 2 points, both on the upstream, nose side of the heliosphere, both at approximately similar distances from the Sun. Nothing is known about the heliopause structure in the downstream tail direction, in the polar directions, or along most of the heliospheric surface. The heliosheath, the termination shock, and the heliopause have been sampled at specific points but not mapped. The most ambitious proposal for addressing this limitation is an interstellar probe, a dedicated mission designed to traverse the heliosphere and enter interstellar space more rapidly than Voyager, carrying modern instruments capable of measurements that the Voyager-era technology could not perform. The interstellar probe concept, developed in detail by a team at the Johns Hopkins University Applied Physics Laboratory, was submitted to the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, which ranked it among the most scientifically important mission concepts for the coming decade. The proposed interstellar probe would use a large solar gravity assist, passing close to the Sun at perihelion, using the Sun's gravity to maximize velocity by launching during a close solar approach, to achieve a speed of approximately 6 to 10 astronomical units per year, compared to Voyager 1's current rate of about 3.6 astronomical units per year. This faster speed would allow the spacecraft to reach 1,000 astronomical units in approximately 50 years, compared to the 300-plus years it would take Voyager 1 to travel the same distance at its current speed. The instruments proposed for the interstellar probe reflect the lessons learned from Voyager. A full plasma instrument suite capable of directly measuring the properties of the plasma in all its phases, including both the solar wind and the interstellar plasma, would address the gap left by Voyager 1's failed plasma instrument, an energetic neutral atom imager, the type of instrument that IBEX uses to map the heliosheath remotely, would provide global maps of the ENA emission from distances that IBEX cannot achieve from its Earth orbit. A neutral gas and dust detector would measure the interstellar neutral atoms and dust grains that penetrate the heliosphere, providing information about the composition of the local interstellar medium. An ultraviolet spectrometer would measure the Lyman alpha background and the hydrogen wall in emission, connecting the in situ measurements to the remote sensing picture built up by Hubble observations of nearby stellar astrospheres. Beyond the interstellar probe, there is a more ambitious concept that has been discussed in the scientific literature. A mission to the heliotail, the downstream tail of the heliosphere, which has never been explored by any spacecraft. The heliotail is where the solar wind that has passed around the heliospheric nose flows back together, and its structure depends on the interplay of the solar wind, the heliospheric magnetic field, and the interstellar magnetic field in ways that are poorly constrained by current observations. IBEX has provided some maps of the tail region from ENAs, suggesting that it is asymmetric and potentially shorter than classical comet tail models predicted. A direct mission to the heliotail would require a different launch direction than any Voyager or planned deep space mission, and would take decades to reach even with advanced propulsion. IBEX itself will be succeeded by the Interstellar Mapping and Acceleration Probe, IMAP, a larger and more capable NASA mission launched in May 2024. IMAP is designed to address several of the key science questions that IBEX raised but could not fully answer. The origin of the IBEX ribbon, the acceleration of anomalous cosmic rays, the structure of the heliosheath as seen from ENAs, and the properties of the interstellar neutral atoms that flow into the heliosphere. IMAP carries 10 instruments, a significant increase in scientific capability over IBEX, and will operate from the L1 Lagrange point, 1.5 million kilometers from Earth toward the Sun, providing a stable vantage point for continuous monitoring of the heliospheric boundary environment and the interstellar neutral fluxes. The New Horizons spacecraft, famous for its historic flyby of Pluto in 2015, is currently in the Kuiper Belt at approximately 60 astronomical units from the Sun, heading outward at about 3.6 astronomical units per year on a trajectory that will eventually bring it to the heliosheath. New Horizons carries an ultraviolet spectrometer that is currently measuring the Lyman alpha background and the heliospheric UV glow from positions in the outer solar system that no other spacecraft currently occupies. Although New Horizons is not on a trajectory aimed at the heliopause's nose region, as Voyager 1 was, and will not reach the heliopause for decades if its power lasts that long, it is providing complementary measurements from the deep heliosphere that fill in some of the spatial coverage gaps that the two Voyager spacecraft have left. The Parker Solar Probe, launched in 2018 to study the Sun's corona and the inner solar wind, is at the opposite end of the heliospheric length scale from Voyager, making close approaches to the Sun at distances as small as 6 million kilometers. But its measurements of the solar wind near its source are directly relevant to understanding how the heliosphere is inflated and how the properties of the solar wind at its origin determine the structure of the heliopause at its termination. The solar wind that Voyager 1 and Voyager 2 are receding through in interstellar space was once the hot plasma swirling in the Sun's corona that Parker Solar Probe is now measuring directly. The two missions, operating at scales that differ by a factor of more than 20,000, are studying different ends of the same structure. The ultimate context for all of this exploration is the question of the Sun's place in the galaxy, not as a fixed point, but as a moving object with a complex and evolving relationship to its environment. The heliosphere is the Sun's personal space, the bubble of its own making that it carries with it through the galaxy, protecting its planets from the worst of the interstellar radiation environment, shaping the properties of the medium that interacts with its planetary magnetospheres, and responding to the varying properties of the interstellar medium through which it moves. Understanding this bubble, its structure, its dynamics, its history and future, is understanding the context in which the solar system exists and has always existed. Voyager 1 and Voyager 2 gave us our first measurements from outside this bubble. They are humanity's only emissaries in interstellar space, sending back data at 160 bits per second, a transmission rate roughly 10,000 times slower than a 1990s dial-up internet connection, from a distance where the light takes more than 22 hours to arrive. That data is still coming in. The mission operations team at JPL still meets regularly to analyze it. Scientists who have devoted their careers to understanding the heliosphere are still finding things in it that surprise them. Conclusion: what it means to have left. In the autumn of 2013, when the announcement was made that Voyager 1 had crossed into interstellar space, the response from most of the world was a kind of distracted acknowledgement. There were news articles, social media posts, a brief flurry of attention, and then the news cycle moved on, as it always does. But what had actually happened was this. For the first time in 4.5 billion years of the solar system's existence, a piece of matter, originating from Earth, had crossed the boundary of the sun's direct physical influence and entered the galaxy. The solar system is not hermetically sealed. Comets and asteroids have been ejected from it throughout its history, and interstellar objects pass through it periodically, as the detection of Oumuamua in 2017 and Borisov in 2019 confirmed. But Voyager 1 was the first human-made object to make the crossing intentionally, carrying instruments capable of measuring the properties of the medium it encountered. And Voyager 2 followed 6 years later, with better instruments still functioning. What they found was not the sterile emptiness that the word void implies. The local interstellar medium is a complex, structured, magnetized plasma with a layered history. The remnant thermal energy of supernova explosions that occurred millions of years ago, magnetic fields shaped by the dynamics of the galaxy's spiral arms, cosmic rays accelerated at stellar death events and propagating freely between the stars, neutral atoms drifting in from distant sources, and everywhere the CMB photons, the oldest light in the universe, permeating everything at a temperature barely above absolute zero. The heliosphere, seen from the outside, is a tiny thing. The entire extent of the heliosphere, the 120 astronomical unit radius bubble that contains all the planets, all the comets of the inner Oort cloud, all of human history, is less than 0.002 light years across. The distance to the nearest star is 4.24 light years. The heliosphere occupies less than 0.5% of the distance between the Sun and its nearest neighbor. In galactic terms, the heliosphere is negligible. In human terms, it is everything we have ever known. The specific measurements Voyager made at the heliopause, the electron density, the magnetic field direction and magnitude, the temperature of the plasma, the cosmic ray spectrum, are not merely data points in a scientific database. They are the first entries in a new chapter of humanity's empirical record. the chapter about the solar system as it exists in its actual galactic context, not as an isolated system in a conceptual void, but as a physical bubble moving through a physical medium with measured properties that determine how it behaves and what lives inside it are exposed to. Ed Stone, the Voyager project scientist, was in his 30s when the missions launched. He has been the project scientist for the entire 47 years since. He has lived to see both spacecraft cross the heliopause. When asked in interviews what he hopes happens next, he has consistently described the importance of building a dedicated interstellar probe, a mission designed from the start for this purpose, with modern instruments, traveling faster, measuring more. That mission does not yet exist. It is in the planning stage, competing for funding against the many other priorities of a space agency with finite resources. The Voyager spacecraft, the only instruments humanity has ever had in interstellar space, are running out of power. The window during which we will have any direct measurement of the local interstellar medium is closing. And yet, the data already in hand is extraordinary. The questions it has raised about the heliosphere's shape, about the acceleration of anomalous cosmic rays, about the structure of the IBX ribbon, about the properties of the hydrogen wall, about how the heliosphere's size and shielding effectiveness have varied through Earth's history, are questions that now have empirical constraints where before there were only theoretical models. The door that Voyager opened cannot be closed. In 1990, as Voyager 1 was leaving the solar system at roughly 40 astronomical units from the Sun, still well inside the heliopause, which it would not cross for another 22 years, Carl Sagan convinced the mission team to turn Voyager 1's cameras back toward the inner solar system and take a photograph. The resulting image showed the Sun as a smear of light scattered by the camera's optics, and in one of the scattered rays, a tiny, barely visible dot. Earth. A pale blue dot, as Sagan named it, occupying less than 1 pixel in the image. The photograph has become one of the most reproduced and referenced images in the history of science communication. "That's here, that's home, that's us," Sagan wrote. Think of the rivers of blood spilled by all those generals and emperors, so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner, how frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Sagan wrote those words in 1994 in his book Pale Blue Dot. They are among the most cited words in the literature of science communication, and their power has not faded. But there is a dimension to them that becomes even more resonant in the context of what Voyager has since told us about the solar system's actual position in the galaxy. The pale blue dot photograph was taken at roughly 40 astronomical units, inside the heliosphere, surrounded by the Sun's magnetic field and solar wind still within the Sun's protective bubble. The solar system, in that image, was still home turf. Voyager 1 took that photograph and then kept going for another 82 astronomical units until it crossed the boundary that even the Sun's own plasma cannot cross, the heliopause. And on the other side, it found that space was not empty. It was full. full of the remnant radiation of the Big Bang, of the magnetic field shaped by ancient supernova, of cosmic rays accelerated at stellar death events, of neutral atoms drifting from directions the sun has not yet faced, full of context, full of history that dwarfs the entire history of the sun. That's here, that's home, that's us, Sagan wrote. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. From 163 astronomical units, the current distance of Voyager 1, even that pale blue dot is invisible. The sun itself is just the brightest star in the sky, not obviously distinguishable from the galaxy's other stars unless you know exactly where to look. Voyager 1 is out there, right now, coasting through interstellar space at 17 kilometers per second, 22 light hours from home, sending data at 160 bits per second to a 70-meter antenna in Goldstone, California. The data describes the local interstellar medium, the medium that the sun and all its planets are moving through, have always been moving through, will continue to move through long after any instrument or civilization is there to measure it. We have measured it, briefly, with 2 spacecraft we launched in 1977 with the computing power of a refrigerator thermostat. The universe, it turns out, was willing to be measured. It had been waiting 13.8 billion years for someone to ask,